So today we are going to finish two very basic identities for decimation and interpolation, which tell us how we can switch the order of the decimation or the expansion with the filters that we employ in downsampling and upsampling. And the advantage of that, as we last talked about, is it helps you build systems which have filters that don't require that sharp a cutoff. So the first identity is for the downsampling operation. And the identity says that if you downsample if you decimate by a factor of m and then you have a filter, let's call that h of e to the j omega xn, and let's call the output after the decimation xan, the output is yn. This is equal to that I do a filtering where the filter is the same filter as the previous filter with just a scaling of the frequency axis by a factor of 1 over m. So h of e to the j omega capital M, and then I do the decimation by a factor of m, xn, xbn, and yn. So that's the basic identity. You can replace the order of, you can interchange the order in which you do filtering and decimation. The only thing you have to do is if you move the filter from after decimation to before, you have to implement, the new filter has to be the previous filter with frequency axis scaled by 1 over m. Okay? And the proof of that is very simple. We just start with writing down, since we already have studied in the last class, what is the frequency effect of just the decimation part. So we can write, let's look at the frequency xb to the j omega. Let's look at that. That is simply equal to the frequency response of the filter times the Fourier transform of the input signal. And now we know, so we know the relationship between xb and xn in frequency. We also know the relationship between y and xbn, which is just decimation. And if you remember from last class, decimation, what it does is just a rescaling of your frequency axis, and there is also a scaling of the amplitude by 1 over m. Right? So the relationship between y and xbn, that is, there is a scaling 1 over m. You get m copies of the Fourier transform, I equal to 0 to m minus 1, xb of e to the j omega minus 2 pi I over capital M. Now I just replace the value of xb there. I get 1 over m summation I equals 0 to m minus 1 h of e to the j omega minus 2 pi I over m times m, and x of e to the j omega minus 2 pi I over m. Okay. Now, of course, I just cancel this capital M with capital M. And in that case, this h e to the j omega minus 2 pi I, that is just saying that you take your Fourier transform of h e to the j omega and you shift it by some multiple of 2 pi. Now what happens if you take the discrete time Fourier transform of anything, any discrete sequence, and you shift it by a multiple of 2 pi? You get back the same thing because discrete time Fourier transform is periodic with a period 2 pi. Right? So this thing is nothing but h of e to the j omega. Shifting by the period is not going to change the output. So I can then simply write down that this is equal to 1 over m times h of e to the j omega, and in the summation I am left with I equal to 0 to m minus 1 x of e to the j omega minus 2 pi I over capital M. And that is simply equal to, I just bring out h of e to the j omega. I write 1 over m summation I equal to 0 to m minus 1 x of e to the j omega minus 2 pi I over capital M. Now, this, of course, this thing inside the parentheses is just equivalent to taking x of n and decimating it by a factor of m. This is simply equal to x of a e to the j omega. So what we get is that y e to the j omega equals x of a e to the j omega times h of e to the j omega, which is what we wanted to prove. Okay. So the effect of this is that if you are given a single downsampling operation, you can actually break it down into smaller downsampling operations. We went over it last time, but I'll just remind you. Let's say someone says that you are required to do a downsampling by a factor of 16. So when you do downsampling by a factor of 16, you first have a low-pass filter which has a cutoff of pi by 16. And then you do downsampling by a factor of 16, xn and yn. Now, according to this identity, I can move this and do change of ordering. So how can I use that identity that I have just proved? What I will do is I will break this low-pass filter into two pieces. So if I am given a low-pass filter which has a cutoff at pi by 16, and this low-pass filter can be equivalently represented as cascade of two low-pass filters, where I first do low-pass filtering with pi by 4, and then I do low-pass filtering with pi by 16. If I'm going to low-pass filter something by pi by 16, I can first low-pass filter by pi by 4, which is a bigger number, and then I can further low-pass filter that. So I can express this filter as a cascade of two filters, where I have a cutoff of pi by 4 and another cutoff of pi by 16. And this decimation operation by a factor of 16, I can also implement that by two decimation operations. I first decimate by a factor of 4, and then I decimate by a factor of 4. So I decimate by a factor of 4, and then I decimate by a factor of 4. And hopefully you all agree that the system on the on the upper side is the same as the system that I have drawn here with 4 components now. Why I have done that? Because I want to use the identity that I proved, and I want to apply that identity on this part. Now that identity that I proved, that says that I can bring decimation first and filtering later as long as I scale my frequency axis by a factor of m. M here is 4. So if I want to do this interchange, I want to bring this filter in the front. If you go back and look at the identity again, the filter at the front is related to the filter before the decimation by simply a scaling of the frequency axis. So if I want to bring this filter before the decimation, after the decimation, I must scale the frequencies by a factor of 4. So if I go back and I say I want to do that, I must then make this filter, the new filter which comes here, I scale everything, the frequency axis, by a factor of 4, which means I get a filter with a cutoff of pi by 4, pi by 16 multiplied by 4. So by doing this interchange, I get this 4 first, and then I get a scaling, which means pi by 4, and the other components stay the same. Now what is the advantage of this system over the one that I started with? That I have now low pass filters which have cutoff of just pi by 4, so they don't have to be that sharp. Okay? And I can actually play the same trick on each of this single component again. This decimation by 4 can be replaced by decimation by 2 times. And this filtering can be replaced by 2 filters. First I do filtering by pi by 2, then I do filtering by pi by 4 cutoff. Of course, the output of this filter or these 2 filters in cascade, they are the same. And then I do decimation by a factor of 2, decimation by a factor of 2. Okay? This is just this block. And I can do the same for the next one. And again, I can say I want to apply the identity to this block, which means I bring decimation first, I bring the filtering later. What do I do to do that? I just scale my frequency axis by a factor of 2, which means that my new cutoff actually becomes pi by 2. So I bring 2 first, the decimation by a factor of 2, and then I do a cutoff of omega c equal to pi by 2. And the other blocks stay the same. So this decimation by a factor of 16, I can implement that using 8 of these blocks, where each filter is only pi by 2 cutoff. Okay? So that's the use of this identity, other than you can play around with this identity to simplify your processing in discrete time. And by simplification, I mainly mean that the filter that you have to design, it doesn't have to have a very sharp cutoff. By doing this manipulation, you can end up with filters which have a very high cutoff. We started with a pi by 16 filter, we ended up with filters which are only pi/2 cutoff. There is a similar identity for the case of interpolation or upsampling. That identity again has very similar expressions. So interpolation identity which says that if you do filtering first, h of e to the j omega, you take its output x of an, and then you do expansion by a factor of m, that is equal to, if you first do expansion by a factor of m, and then you do filtering, as long as the new filter that you have, its frequency axis is scaled by a factor of 1 over m. Again, the solution or the proof of this is rather simple. If we look at the Fourier transform of y of n, y e to the j omega, that is simply the expanded version of xan. And if you remember from previous class, when we do an expansion by a factor of m, the only thing that happens is you have a scaling of the frequency axis by 1 over m. Right? So you get x of a e to the j omega capital M. Expansion in time, your frequencies get compressed, scaling by a factor of 1 over m. Now let's just take xa and figure out what that is. That is simply equal to the input x e to the j omega m times the frequency response, which is h e to the j omega m. Now if I look at this x e to the j omega m, that is simply a scaled version of the frequency of x by a factor of 1 over m. So that is simply the Fourier transform of xbn. If you just have to keep in mind what is the relationship between input and output when the frequency axis is scaled by a factor of m or 1 over m. In this case, it's being scaled by a factor of 1 over m, so it has to be just an expanded version of xn. So this is simply xb e to the j omega h of e to the j omega m, which is of course this thing. And what is the use of this interpolation identity? Exactly like we talked about in the case of decimation identity. In interpolation in general, your cutoff is pi over m. If I say I want to upsample by a factor of 16, in the usual way, I will have to implement a cutoff of pi by 16, but using the same trick that I did for decimation, I can actually implement that either with pi by 4 filters or pi by 2 filters. It's exactly the same exercise, so we won't go over that in detail. So that finishes up our discussion about decimation and interpolation. What does decimation do to the frequencies of the input signal? What does expansion do to the frequencies of the input signal? So just to remind you, we have been, for the discrete time, we have been doing these operations. We have only looked at two kinds of operations in discrete time systems: filtering and either decimation or expansion. Okay. So we had this operation, we have some filter, xn, yn. We know what is the effect on frequencies. Simply the frequencies of the input signal get multiplied by the frequency response of my filter. The other operation we looked at is simply decimation by a factor of m. And we understand what is the effect of that on the system. We get m copies of the input frequencies. The frequencies get scaled by a factor of m. And there is a scaling of the amplitude by a factor of 1 over m. Okay. And we also saw the case of expansion, which is the input frequency simply gets scaled by a factor of 1 over m. So any system which has these three components in any order listed, you can start from the input and keep on traversing, and you can say, what will be my output frequencies? Okay. We have sort of done the same in continuous time, except a couple of things. In continuous time, we haven't really said the relationship, we haven't set up the relationship between the continuous time frequencies and the discrete time frequencies. Okay. That's the only remaining piece that is left. For example, if I am given a continuous signal x of t and I sample it every t seconds, I get xn. What is the relationship between the frequencies of xn? So how is xe to the j omega, which is the dtft of the sequence, related to x of j omega, the continuous time Fourier transform of the continuous time signal? Similarly, we haven't discussed that if we start with a discrete sequence and we have convert to impulse train, to it for impulse train with a period t, where we get x of st summation of xn delta of t minus nt. We haven't discussed how is xs j omega related to x of e to the j omega. Okay. Other than that, we sort of know the relationships. We know, for example, the relationship between xt and xst, which is this impulse sample version of your signal. So if we can figure out these remaining pieces, then we have all the information that we need for frequency domain interpretation of digital systems from input to output. The systems can have sampling operators going on, filtering going on, perhaps some sort of decimation, expansion. You can just keep on traversing each block according to our understanding of frequencies, and at the end of the day, you have an input-output relation in frequencies. Okay. So what we are going to do is study first how does sampling, and by sampling now I just mean this pointwise sampling, closing the switch. How does pointwise sampling affect the frequencies? To do that, let's remind ourselves of a few things. One is that we had talked about this abstraction of this operation xn, as we had said that is mathematically equal to, you get x of t, you multiply it with this impulse train s of t delta of t minus nt, and then you take this xst and you convert it into samples or sequence, and you get xn. Okay. So what we have is that XST, the way we write that, XST is nothing but summation of n, x of n t delta of t minus nt, and x of nt is of course just the sequence xn. X of n delta of t minus nt. So let's take its Fourier transform now. X of e to the, not x of e to the, it's a continuous time signal, so x s of j omega, that is simply Fourier transform of this summation n x n delta of t minus nt. Now since the Fourier transform is a linear operation, I'll just take it inside the summation. Xn is just a scalar for the continuous time Fourier transform, so I'll have Fourier transform of delta of t minus nt. Now what is the Fourier transform of delta of t minus nt? It's simply an exponential e to the minus j omega nt. So this is something, an equation which we will call star. Now let's look at the Fourier transform of xn. Well, for that we just have to use the standard DTFT formula, that is summation of n x of n e to the minus j omega n. Let's call that double star. So if we compare star to this double star equation, what do we see? That x of e to the j omega is the same as, so if we compare this expression to the one above, we see that x of e to the j omega is exactly xs j omega. The only difference is that instead of little omega, it has capital omega t. In other words, the discrete time Fourier transform of my sequence is simply the continuous time Fourier transform of this xst with capital omega replaced by little omega over t. If I simply replace this capital omega by little omega over t, I get back the x e to the j omega. Or I'll write that as xs j of little omega over t. So what does that say? That even though we have, when we do the sampling, we don't really get this xst, but in terms of understanding the discrete time Fourier transform of my sequence that I obtained by doing this pointwise sampling, that is simply equal to the continuous time Fourier transform of this xst, where the axis is scaled by a factor of t. Instead of omega, I have omega equal to little omega over t. So we have a scaling of the axis. Okay. Now, let's also remind ourselves, one of the first things that we did was ask, what is the relation between xs j omega and the input x j omega? The relationship that had come out was that xs j omega simply consists of multiple copies of x j omega, my original signal, x of j omega minus 2 pi k over t, and there is a scaling of the amplitude by 1 over t. So we know this fact. How is xs related to the input signal in terms of frequencies? We get multiple copies of our input signal, and they are all scaled in amplitude by 1 over t. And now we know the relationship between xs and xn, which is simply a scaling of the frequency axis. So I can write then x of e to the j omega. I just take this and I plug in little omega over t, and I get 1 over t k minus infinity to infinity x of j little omega minus 2 pi k over capital T. So when we do pointwise sampling, this is effectively what is happening. This is for the case, now I can just forget about how I got to this. This is for the case that I take input signal x of t and I get back the sequence xn. And the relationship is this. Let's try to decipher this relationship. We have first this factor of 1 over t. So the first thing that happens is that scaling of the amplitude by 1 over t. The other thing is that we get multiple copies of our continuous time signals Fourier transform, where each copy is scaled. This is scaling of the frequency axis scaling by capital T. And then each of those copies is shifted by a factor of 2 pi. That's the shift. Shifted by multiples of 2 pi. So if we are given let's draw the typical diagram. If we are given this signal, and let's assume that this is pi by t, and the height is a, this is the Fourier transform of my input signal, and I sample it. Well, according to this formula, what we get is, first of all, the height gets scaled by a factor of 1 over t, so all the spectrum will have a height of a over t. And then we'll have different copies where each copy is scaled by a factor of, the frequency axis is scaled by a factor of capital T. So we'll have a scaling of this thing where this point gets this will be now at pi, and this will be at minus pi. Okay. And then we will have multiple copies where each copy is shifted by 2 pi. So we'll have the same thing at 2 pi, at 4 pi, minus 2 pi, and minus 4 pi, and so forth. Okay. In particular, if you look at it, assuming no aliasing, right? What is the highest frequency that your continuous time signal can have? it can have a highest frequency of pi by t radians per second. That pi by t radians per second highest frequency gets mapped to the highest frequency in discrete time. What's the highest frequency in discrete time? Pi. So this pi by t gets mapped to pi. If you have any frequency which is higher than pi by t, that would have aliased, and that would appear in the range of minus pi to pi. But the general principle remains, if this had gone beyond pi by t, you will have scaled this beyond pi by t and then added all of them together. And then you will get something which doesn't really look like the original signal. It will have this aliasing happening. Okay. In general, an easy way, if you ever forget which way the scaling goes, remember in continuous time your units are radians per second, and in discrete time your units of frequencies are radians. So how do you go from radians per second to radians? You have to multiply with by t so that you get to radians. So that is the relationship between the input and output signal when you do sampling. Now, if you want to ask about the other way around, which is you are given a sequence xn and you convert it to an impulse train, xst equals summation of xn delta of t minus nt. Well, again, the same relationship that we saw earlier holds. The relationship, if you want to find out what is the Fourier transform of xs j omega, that is simply equal to the Fourier transform of x e to the j omega, with now scaling happening in the other way, little omega replaced by capital omega t, which is simply x e to the j capital omega t. Okay. So when you go from continuous time to discrete time, your frequency axis gets scaled by t, so that you go from radians per second to radians. When you are going from discrete time to continuous time, you have a scaling of the axis by a factor of 1 over t, so that you go from radians to radians per second. Okay. That is about the only thing that we have left to do as far as understanding in frequency domain what happens with different blocks in our digital systems. Now, if we are given any system with different kinds of components, we can simply go through them one at a time, and we can write down the final input-output relationship. So we'll try to do that for a general case, and then look at the special example of when we only have a band-limited signal. So let's now, armed with all of these expressions, let's ask ourselves, I'm not going to, by the way, in these block diagrams include the diagrams of either the blocks of either decimation or expansion. If they come up, you can easily incorporate them. Okay. Right now, I'm going to ignore them. So let us examine the effect of the following digital system on the input frequencies. And right now, all that I'm going to express, I'm not assuming any signal model. I'm not assuming anything about band-limited nature of inputs or filters or anything. Okay, we'll try to be as general as possible. So we have an input signal x of t. After that, we typically have a filter. That filter could be doing many things depending upon the signal model you are assuming. If you are assuming band-limited signal model, then this filter will be just an anti-aliasing filter. But right now, I'm not going to specify what filter that is. The output of that, I'm going to call xs of t. And after that, I have the sampling operation. The output of that, I'm going to call xn. Now, typically in the discrete time, once you you are looking at a sequence, you filter it further in discrete time to implement some operation. Let's say you are given an image and you want to sharpen it or you want to blur it. So we have a discrete time filter. The output of that, let's call yn. Now, once you take your output, you have done the processing, you typically want to convert it back into a continuous time system. So we convert that to impulse train. We get ys of t. And the final process after that is there's typically an interpolation filter, which we have called post filter or reconstruction filter. Let's call that hr of j omega. And we finally get back y of t. And what we want to understand is what are the frequencies that are present in y of t as a function of the input frequencies and all the other components in the system. Okay. Now, when I'm converting to impulse stream, I'm implicitly assuming that I have a factor of t here. Okay. And here I'm doing it in a pretty general nature. I also want to make sure that we clarify which of these components, since your book uses a little bit different expression, which of these components relate to which components of the description in your book. So in your book, this thing, t equal to nt, the ideal sampling, this is denoted by continuous to discrete, capital T, okay? So when I use this or I use this block diagram, they mean the same thing. Similarly, in your book, this expression that you have a sequence, you convert it to impulse train with a period t, and then you have a reconstruction filter, which is an ideal low-pass filter with a cutoff of pi by t and a height of t. So hr j omega equals minus pi by t to pi by t and a height of t, this thing. When this condition is satisfied, when hr j omega is an ideal low-pass filter with a height of t, in that case your book uses the notation discrete to continuous and capital T here. Okay. Just want to be sure that we can do the translation between these blocks in your book and the blocks that I am using. Okay. So right now, though, we are not going to assume anything about hr j omega. We just want to write down the output y of t in terms of its Fourier transform. So to do that, let's just traverse one block at a time in frequency domain. All of these operations, as we have seen, we can very well identify what happens to the frequencies. So let's look at, first of all, the first block. Let's ask ourselves, what is xsj omega, which is the output of this first block? That is simply old knowledge, input frequencies multiplied by the Fourier transform of my impulse response. So that takes care of my, up to this block, my output is this. Let's now ask what happens after that. So this is the first block. The second block is this sampling operation. We have just done that. What's the relationship between the input and output of this sampling operation? We know that x of e to the j omega is simply equal to scaling of the amplitude by 1 over t and multiple copies of the input, and the input is now xs, and scaling of also the frequency axis by a factor of t, so omega minus 2 pi k over t. Now I just input the value of xs, so I get x of e to the j omega equals 1 over t summation of k x of j little omega minus 2 pi k over t and hs of little omega minus 2 pi k over t. Okay. So I've just input the value of xs from this first block output. Okay, let's move on to the next block. So the next block is the relationship between the output of this discrete filter. Well, again, that we know, the output of this discrete filter in Fourier domain is simply multiplication of the frequencies of the input times the frequency response of my filter. So the third block input-output relationship is y of e to the j omega equals x e to the j omega times h e to the j omega. Once again, now I just input the value of x e to the j omega. I get 1 over t h of e to the j omega summation of k x of j omega minus 2 pi k over t hs of j omega minus 2 pi k over t. Now let's look at the next block. The next block takes the input, a discrete sequence, and it converts it into the impulse train. And again, we know the relationship between the input and output of the impulse train. This conversion into the impulse train is just a scaling of the frequency axis by a factor of 1 over t. So the fourth block is asking for the relationship between the output, which is ys of j omega, and the input, which is y of n. And that relationship is simply a scaling of the frequency axis. Okay. So we just take whatever is y of e to the j omega, and we just scale the frequency axis by a factor of 1 over t. And now I just replace everything that I have written up there with little omega replaced by capital omega t. So I get 1 over t h of e to the j capital omega t summation of k. When I replace this, I get j of omega minus 2 pi k over t hs of j omega minus 2 pi k over t. What is the last block that we have to worry about? That is the reconstruction filter. That is just a filtering problem, which is again given by the output is simply the frequencies are scaled by the frequency response of my filter. So the final block is that my output y of j omega is simply ys j omega times the reconstruction filter hr j omega. And now I just replace that, so I get 1 over t h of e to the j capital omega t hr of j omega summation of k x of j omega minus 2 pi k over t hs of j omega minus 2 pi k over t. This is the final expression that you get regardless of what kind of sampling, what kind of assumptions you are making about your pre-filter, post-filter, whether you are saying it's a band-limited signal or not. If I were to introduce perhaps a decimation or an expansion operation in there, I could have done the same with that. I will have some more factors here. So this shouldn't be ys, this should be y of j omega. Up to this point, we have said let's keep things general as general as possible. Now let's look at the special case of band-limited signals. And let's ask ourselves, what does this expression reduce to if we are doing sampling under the band-limited signal model and we have no aliasing? So let's look at that. Let us specialize to the case of number one, band-limited signal model. Which means that x of j omega is equal to 0 for all omega which are bigger than pi by t. Now, if you think about it, since I'm assuming the signal to be band limited and I have a filter before that, regardless of what the filter's endpoints are, once I have a band limited signal, I multiply that with that filter. I only care about the range of frequencies between that band. If I have a band limited signal, let's say minus pi by t to pi by t, and I pass it through a filter, so this is my x of j omega, I pass it through a filter x s j omega, which goes to, let's say, pi by 2 pi by t to minus 2 pi by t to pi by t, 2 pi by t. It doesn't matter if this filter goes up to 2 pi by t because I'm going to pass it through, I'm going to only pass a band limited signal through this, so I can, for all purposes, all intensive purposes, I can just assume that this filter actually ends at pi by t. Because having the range of this filter beyond pi by t, we don't care. It's going to not impact my input signal anyways. My input signal is just band limited. So this automatically implies for the band limited signal model that hs j omega without loss of generality, I can assume that that is equal to 0 for all omega greater than or equal to pi by t. I made a typo here. It shouldn't be less than or equal to pi by t. It should be greater than or equal to pi by t. So our specialization involves a band-limited signal model, and the other thing we are going to assume is we have an ideal low-pass filter. HR j omega is t times indicator from minus pi by t to pi by t of omega. It means it just looks like an ideal low-pass filter with a cutoff of pi by t, and its height is t. So let's do this analysis that we did above under this model. So I just replaced HR j omega by this expression. Okay. So I get y of j omega. I'm just looking at the boxed version, and I'm going to write that as 1 over t h of e to the j omega t multiplied by t times the indicator function minus pi by t to pi by t of omega times I have this whole summation of x of j omega minus 2 pi k over t and hs of j omega minus 2 pi k over t. So of course this t cancels with this t. Now I'm going to write these indices which go from minus infinity to infinity as the index for k equal to 0 and k not equal to 0. So at k equal to 0, I get h of e to the j omega t times one indicator function minus pi by t to pi by t of omega. At 0, it's just x of j omega and hs j omega plus summation of k not equal to 0, x of j omega minus 2 pi k over t times hs j omega minus 2 pi k over t times the indicator function minus pi by t to pi by t omega. Okay. So if we now look at this part, of course x and hs, they go up to pi by t but no further, right? And this one indicator function is from minus pi by t to pi by t. So this is simply equal to x of j omega hs of j omega. But if we look at this expression, each term inside the summation, this thing is just x j omega h j omega shifted by a factor of 2 pi k over t, which means that x of j omega minus 2 pi k over t times hs of j omega minus 2 pi k over t, this is exactly equal to 0 for all omega between minus pi by t and pi by t. So any of this for k not equal to 0, we have that these terms are 0 between minus pi by t and pi by t. But outside pi by t and minus pi by t, this indicator is 0. So this whole summation becomes 0 because we are multiplying two functions. One lives outside minus pi by t to pi by t. One lives inside minus pi by t to pi by t. So the multiplication of them becomes 0. Each term inside becomes 0. So what we get is that y of j omega is simply equal to x j omega hs j omega times h of e to the j omega t and the indicator function minus pi by t to pi by t of omega. Okay. Now this thing, I'm going to call it age effective j omega. Okay. And I'm defining it as h of e to the j omega t for omega less than or equal to pi by t and 0 otherwise. That's just the definition. I've just expanded that into its proper expression. Okay. So what we get is that y of j omega is simply equal to xj omega hs j omega times h effective j omega. If we focus on this expression, which is only, again, keep in mind, which is only valid if we are dealing with band limited input and our reconstruction filter is an ideal reconstruction filter. If we look at this expression, at least mathematically, this expression is equal to as if we had an input x of t, so that is xj omega. What happens after that? We filter it with a transform with a frequency response hs, which of course we were doing before. But after that, there is another frequency response which is called h effective of j omega, and we get back y of t. Okay. Now let's try expanding that. What was that equal to? That was equal to, if you remember, that was equal to this sampling, t equals to nt. That was it. Then we had this filter h of e to the j omega, and then we had this conversion to impulse train. And then we had hr of j omega. Effectively, what this is saying is that the effect of doing sampling, filtering in discrete time, and then converting back to continuous time is equivalent to as if you just were filtering your continuous time signal by a filter whose Fourier transform is related to the Fourier transform of your discrete filter. What is the relationship? The Fourier transform of your effective filter is simply, if you look at within pi, you just scale your Fourier transform of your discrete filter by a factor of 1 over t, and then you just look at between pi by t and minus pi by t and pi by t. So for example, if my h e to the j omega was like this, let's say my h e to the j omega was low pass filtering to pi by 2. Periodic copies, and the height was, let's say, b. What this expression is saying is it will be equivalent to that instead of this filter, as if, even though you are not doing that, as if you had just a continuous time filter whose frequency response was simply given by, you just scale this. So this pi by 2 becomes pi by 2t. There is a scaling by a factor of 1 over t. Okay. So you have a scaling of your frequency axis, no scaling of amplitude. You have a scaling of your frequency axis, pi by 2t minus pi by 2t. Okay. And then you don't look, so these repeated copies, of course, are after pi by t. So you would not incorporate those. So this is the Fourier transform of your H effective j omega. So a low pass filter in discrete time is equivalent to a low pass filter in continuous time with just a scaling of where the cutoff is. If you want to implement a low pass filter in continuous time, you can do that inside your computer as long as you can match the frequencies accordingly. Let's say you want to do low pass filter at 2 kilohertz. The cutoff frequency of your discrete time filter will be 2 kilohertz multiplied by t, your time period. Or if your discrete time system was doing a cutoff at pi by 2, in continuous time that is equivalent to as if you were doing filtering with a cutoff of pi by 2t. Okay? So a simple scaling of the frequencies, no scaling of the amplitude. Okay? The key though is A, you have to have a band limited signal, and B, your reconstruction filter has to be ideal. Otherwise you are back to this expression and you have to look at how close this expression. So you are back to this bigger expression and you have to look at how close that big expression is to what you want. Okay. But oftentimes we are willing to make the approximation that it is almost doing the same, and we just say the discrete system is just implementing a continuous time filter. And we just figure out the relationship between the frequencies of the two filters through the scaling of the frequencies. Just to make sure we also relate it to the same picture that your book uses. As I said earlier, your book sort of uses then this picture. You have 1 over t, which is for this. Then you have the filter, h of e to the j omega, and then you have for both of these things with the ideal low pass filter, you have discrete to continuous t. So this is equivalent, and what this means is that the input-output relationship between these three block diagrams is equivalent to that you have y of j omega equals x of j omega times h effective of j omega. Again, assuming that you are doing band limited signals. And when I draw this D to C with this like this, it automatically assumes that you have an ideal reconstruction filter. So what will happen in real world is someone will say that they want you to implement, you have this continuous time signal, and someone wants you to do some sort of an operation, typically described in terms of frequencies. And the way you do that is you digitize that system, and the only thing you have to then worry about is assuming that all your reconstruction filter is ideal, your input was band limited, you have to only worry about how do you figure this discrete time filter properly. And we of course know what is the relationship in frequencies. You can also, since in digital systems you often can give the impulse response of your discrete system, you also could ask, okay, is there a simpler way of going to the impulse response of this filter? So of course, h of e to the j omega has an impulse response hn, and you can first take your effective filters frequency transform, go to the discrete filter, and then take an inverse DTFT. But is there a direct relationship between the impulse response of the continuous time filter and the impulse response of the discrete time filter? Okay. And the answer is, of course, yes. It is called impulse invariance, which means that if you are given two filters, which are related to this way, that you have age effective j omega equals to age of e to the j omega t for omega less than or equal to pi by t and 0 otherwise. Then the relation, and this age effective j omega has, let's say, impulse response age effective t. How is that related to the impulse response of, what is the relationship between this and hn, which is the Fourier transform of age of e to the j omega? And the answer is, it's simply given by samples of your impulse response. hn is samples of your effective impulse response multiplied by t. Okay. So if someone says, I'm interested in, give me just the impulse response, because in my MATLAB I can just run the convolution expression as it is, you simply take the impulse response of your continuous time filter and you just sample it every t seconds and you multiply it with t, and the relationship that you will get between their frequencies will be this relationship. And why is that true? It follows simply from the earlier analysis that we did between the frequencies of sampled and continuous time signals. So to prove that, I can just say, let's take h prime n, another sequence, as age effective of nt. Okay? So now just think of this age effective t as a signal. We don't care whether it's an impulse response or not. It is a continuous time signal. So if I sample it every t seconds, so what I'm doing is just this block. I have age effective of t, and at the output I'm calling it h prime n, and I'm sampling it every t seconds. And I know what is the input-output frequency relation. Right? We just did that earlier in the class. The relationship is simply, I get multiple copies of my input signal, hc of j omega over t minus 2 pi k over t, or age effective k. But what we want is the relationship that we have between the two, between the continuous time and the discrete time filters, is that age effective of j omega over t minus 2 pi k over t is equal to age of e to the j omega. Okay, so there is no scaling of 1 over t. We want the frequency response of both the filters to be exactly the same, except a frequency scaling of the frequency axis, but no scaling of the amplitude. So what is the relationship of h e to the j omega to h prime e to the j omega then? This implies that h e to the j omega is simply equal to t times h prime e to the j omega. And now I take their inverse Fourier transform, which means that h of n is simply equal to t times h prime of n, which is simply t times h effective of nt. Okay. So if you are given, again, just to make sure that we remember, this discussion is about the equivalence of these blocks with a continuous time filter. Okay. The way to go between them is a scaling of the frequency axis. Another way is we can also look at their impulse responses, and the impulse response of the discrete filter is simply t times the samples of the impulse response of the continuous time filter. Okay. Now in the same expression, as I said earlier, we can keep on adding either decimation or interpolation or any other components. But as long as we understand the relationship between the inputs and outputs, we can, from one end to the other end, we can concretely specify how will the frequencies of my output signal look like. Okay. That is about all that I want to say for continuous time one-dimensional signals. I'm not going to talk about things like quantization because I presume you know that from your undergraduate. You can do the revision from your text. But quantization, I'm not going to spend too much time. Actually, no time on it.